All right, so in order to solve this first inequality, we are going to subtract 4 from both sides. That gives us negative 4x is greater than 16. And then the other thing we have to do here is divide both sides by a negative 4. And when you do that, you get negative 4 and x. But whenever you're multiplying or dividing by a negative, you have to change the sign. So make sure you remember to do that. It's one of the small little differences with these inequalities. Make sure that you do change the sign. As far as the number line goes, if this is 0, negative 4 is over here. X is less than that, not less than or equal to. So it's going to be an open circle. And since it's less than, it goes to the left. In interval notation, we'd say that's negative infinity to negative 4. It doesn't include negative 4, so a parenthesis there. And then as far as the set notation goes, this is just another way to write a range of answers. So we're going to put these fancy little brackets on there. All the x's such that x is less than negative 4. Fancy bracket to close it. And there is our set notation. There's other small little differences in the way we can write this, but this is the general idea. We are going to be focusing on the interval notation. But if you see this, don't freak out by it. You might see like in a standardized test or a multiple choice or something. These mean the same thing. It's just a different way of saying the same thing. Okay, to the right. You have 3 parts to this one. There is a left, a middle, and a right. And what we're going to do instead of just to the left side and the right side, we're going to do to all 3 parts. To begin with, divide everything by negative 2. So that's 3, x plus 2, and negative 5. But again, because we divided by a negative, make sure you change all of those signs around. Then subtract 2 from everything. And now we have x all by itself. X is sandwiched in between 1 and negative 7. So on the number line, here is 0. 1 has a filled in dot. Negative 7 has an open dot. And we need to be between those values. So this is what our graph is going to look like. An interval notation then that goes from negative 7 to 1. And set notation. The set of all x's such that negative 7 is less than x is less than or equal to 1. And that's what it's going to look like in set notation. So a little bit of review and just solving the linear inequalities. We want to make sure that we do all the algebra we would normally do. But when you're multiplying or dividing by negative, that's when the sign changes sides.
Now for, could I multiply the negative 2 times x plus 2 first? That'll work.
Okay, so here's our newer stuff. The goal here is to solve each inequality. Smaller to bigger. Yep. And those problems were linear. Everything was x to the first. And there were a couple small catches as far as switching the sign maybe, or there's 3 different parts instead of just a left and a right. But now we have 3 different binomials that are multiplied by each other, and it's greater than 0. Now, I could multiply all this stuff out, but that would be a big mistake. That would be complicating the problem. It'd be x cubed plus a bunch of other things. Instead, in this factored form, things are going to be much smoother for us in trying to solve this inequality. I'm trying to figure out what x values can we plug in so that when you run it through this, you get a response, you get a result that's greater than 0. Like I can do trial and error. Could I plug in 20? Is that going to work? Could I plug in negative 20? Is that going to work? Instead, we're going to be a little more methodical about it. And this is right now written as a product of linear factors. There was a question on the quiz about that. Some of you really struggle with that part of it. If you know what your solutions are, you can write them like this. And this is called a product of linear factors. Product because they're multiplied, linear because everything is just x to the first. Now, I'm going to use this to my advantage and say there are zeros at x equals 1, x equals 3, and x equals negative 3. So I'm going to the number line. Those are zeros. They're roots. They're solutions. If it was just equal to 0. Because it's greater than, but not greater than or equal to, these are all going to be open circles. And then this gives us the start for how we can figure out where these solutions are going to work. I'm going to look at this region that's to the farthest left, and there's a lot of numbers that are to the left of negative 3. -4, -5, -20, even -3.1. There's a lot of numbers that are in there. But they're all part of the same region. If one of them works, they're all going to work. If one of them doesn't work, then none of them are going to work. So I'm just going to pick any number. For example, what if x equals -4? It's just one of the numbers from that region. And then I'm going to plug this into the inequality without paying too much attention to precise details. In other words, -4 minus 1, yeah, I know that's -5. More importantly, it's a negative. And then -4 plus 3 is another negative. -4 minus 3 is another negative. And the reason why we can do that and not have to be terribly precise is because we're just comparing this left side with 0. We don't care how big this is exactly. It's just, is it bigger than 0 or not bigger than 0? So when I take a negative times a negative times a negative, it's going to be a negative result, right? Is a negative number greater than 0? It isn't. So I'll give myself a little note. Unfortunately, that doesn't work. -4 doesn't work. And in fact, any number in that region, like if I plugged in -5, we would still have a negative times a negative times a negative. And it's not going to be greater than 0, so this region is not going to be shaded in. The next region, I need to pick a number between -3 and 1. A good candidate there would be like x equals 0. And again, the beauty of having it in this factored form is I can look at these different parts that are multiplied by each other. 0 minus 1 is negative, 0 plus 3 is positive, and 0 minus 3 is another negative. So any number in that region, we'd get the same values. And then a negative times a positive times a negative, that is greater than 0. So yes, that works. Which means this whole region then is going to be shaded in. Next region between 1 and 3, good candidate would be like x equals 2. 2 minus 1 is positive. 2 plus 3 is positive. 2 minus 3 is negative. A positive times a positive times a negative is negative, so it is not greater than 0. It doesn't work, so it's not going to be shaded. And after you've done a few of these, you start to ask yourself, what am I anticipating in the next one? So something to the right of 3, like maybe like x equals 4. Do I think it's going to work or not? I kind of think it will. It didn't. It did. It didn't. I think it probably should. So if I plug 4 in, 4 minus 1 is positive. 4 plus 3 is positive. 4 minus 3 is positive. Positive times a positive times a positive is a positive value. So yes, it's greater than 0. So yes, it gets shaded. So now the number line isn't the final answer, but by building this number line, it helps us to determine where is the solution. So we're going to say any number between -3 and 1, but not including those points, parentheses, because it was just greater than. If you actually plugged in -3 or 1, you'd get 0 on the left, and 0 is not greater than 0. So we could either have this part union, which is saying or, it could be anything from 3 to infinity. And we're not going to write in set builder notation, just this interval notation gets the same idea across. These are all the solutions. There's an infinite number of answers that are in this region or in this region, and there's no way we could list all of them, so we list them in this interval notation, just like in this range. Any number in between either this or this to infinity would work for us. So the fact that it's multiplied out, this product of linear factors, was hugely important for us, because then we could just pick the regions and determine if it was true or not true. All right, so that one is already multiplied out for us. To make it more relevant to where we're at with our skills in pre-calculus, we have this polynomial now, this cubic, x cubed minus x squared minus 32x plus 79 is less than or equal to 19. Our goal is to solve to figure out where this works. And as I look at this problem at the beginning, I see the right side, it is 19. And it's definitely to our advantage to make the other side equal to 0. Like just that whole positive negative test that we were doing. It's nice when there's 0 on the other side, because 0 is the great split between the positive and negative numbers. 19 isn't. So subtract 19 from both sides. which leads us to this polynomial on the left. And here's where we use the calculator to our advantage. It is x cubed, so I'm expecting to get 3 roots to this one. The last coefficient, the constant number is 60. So this gives me an idea of what might be the possible integer solutions. Any factors of 60 might be a 0 here. And really good news for us is it's a 1x cubed, which with that rational roots there means we don't have to worry about fraction answers. I don't have to go into my calculator and do a delta table as 1 over any other number. We're just looking at the integers. So our strategy here is enter the equation, then look at the graph. Look at the graph. We're expecting it to cross 3 times. Hopefully it does. If not, we might need to expand our viewing window, or the answers might be some imaginary ones, which wouldn't work for this. But I'll enter in the equation, look on the graph. That'll give me an idea of where to look, and then go to the table and try to figure out what x values are roots to this one. And we're starting off with a really nice one. If this one were on a quiz, these are really friendly numbers to work with. Again, expecting 3 solutions. I believe -6 is one of them. When you plug -6 in for x, you're getting an output y value of 0, -6 and 2 and 5. So 3 roots. Because it's x cubed, we have all of them. So we can use our calculator to find those roots. Then we're going to write this polynomial, this left side, as a product of linear factors. It's going to be x minus -6, x minus 2, and x minus 5 is less than or equal to 0. And now the problem looks exactly like the previous one. The numbers are different, but it has the same idea to it. It's in factored form. So what you need to do is get the number line ready to go. You have at +5, at +2, and at -6, there's 0. Because it's less than or equal to, this time they're going to be closed in dots. And then you want to check the regions. Check the regions. Check the region all the way to the left first, or you can go all the way to the right. It doesn't matter. I like to go methodically left to right, so I'm going to check something over here like -7. -7 plus 6 is negative. -7 minus 2 is negative. -7 minus 5 is negative. And a negative times a negative times a negative is less than or equal to 0. Yes, it did satisfy that. Now we want things less than 0. So that is going to be shaded. Go ahead and check the other regions. The nice thing about this is usually there's a lot of symmetry. It works, the next region doesn't work. The next region works, the next region doesn't work. That's usually going to happen. We'll see some examples when it doesn't, so we can predict when that's going to happen. I'd encourage you to check each one of those, because if you made a mistake on the first one and you just assumed it was every other, then you're going to be way off on that one. So check the other ones, make sure they agree, but at least you know what to expect. You can either shaded, non-shaded, shaded, non-shaded, or the converse of that. Christian, what number did you try next? X equals 0. Did it work?
I don't
No,
know.
didn't work. Anybody get between 2 and 5? Did it work?
Yeah.
And I kind of expected it to. And then the last region, something bigger than 5, like 6. Expecting it probably not to work. Did it work? No. So we can get an idea again of like, I think I know the pattern. And when you try those, something between 2 and 5, maybe like 4, something between bigger than 5, maybe like x equals positive 7, you're going to get yes, you're going to get no, checking those different values. So then in interval notation, we're going from negative infinity to negative 6, union 2 to 5, and I should have brackets on all these because it is the or equal to, but with the infinity, that's always going to be parentheses. Okay, so find those zeros, write it as a product of linear factors, and then check those regions. Let's skip over this one. All right, let me give you the next one. 3x cubed minus 31x squared plus 113x minus 72 is greater than or equal to 23x. So the reason why I'm giving you this one is because now the leading coefficient is a 3. It's a 3x cubed, which means you might be getting some fractions. Step 1, enter the equation into your calculator because that's going to help speed things up by quite a bit. And know that you might very well be getting some fractions. In fact, you probably will. Since the leading coefficient is 3, you go into the table setup and have the delta table set to 1 over 3. Use your graph to tell you where to look. Once you have it as a product of those linear factors, then check the regions to see where this actually works.
Do you know the closest open one is?
You just sign off first.
Oh. Do I have the same sheet?